So we get it kind of equal to 0. We tee it up. We get our two roots, 5/2 and -3. Okay? Now, the thing with inequalities is that you always have an infinite number of solutions. Your solutions with inequalities, since you've done linear inequalities in Algebra 1, have always been kind of displayed via shadings on a number line, right? Do you remember all that stuff? Okay? This is no different. So, except for the fact that we have two kind of roots. So 2.5, which is here. And is that going to be an open circle or a closed circle? Is that point in and of itself, is that x value a solution? Does it make it greater than 0? No, it makes it equal to 0. So we're going to use an open circle at 2.5. I'll put 2.5 because that's 5/2. And another open circle at -3. So that's where our polynomial actually equals 0. And so it's created really 3 different intervals of space from -infinity up until -3, between the two, and then from 2.5 up to infinity. And we have to figure out which of those intervals work. Sometimes the two intervals on the outsides work. Sometimes the interval in between works. Sometimes, as you'll see, depending on problems, like both sides of a specific 0 would work. So you just essentially plug in points. And again, do not get wrapped up in the actual value. We want to see, let's say we test -4. And I would always recommend plugging in to this one to check. Because when you plug in -4, is this first factor going to be positive or negative? We seem to have a disagreement there. Do that again. When you plug in -4 to this first factor, are you going to get positive or a negative? Negative. You're going to get -8 minus 5. Who cares what it is? It's a negative number. When you plug in -4 here, are you going to get a positive or a negative? Negative as well. So when you multiply a negative times a negative, what do you get? A positive. Is a positive greater than 0? Yes. So this is a solution, and therefore you would kind of shade in towards -infinity. All of that are solutions. Then plug in something between. 0 would probably be the easiest to plug in. When you plug in 0 here, you're going to get a negative. When you plug in a 0 here, you get a positive. A negative times a positive is a negative. Is a negative number greater than 0? No, so that's out. And then plug in something greater than 2.5, like a 3. That's going to give you a positive times a positive, which is a positive. Positives are greater than 0, so that's also a solution set. So your solutions, and first I have up here in set builder notation, is the set of all x's such that x is less than -3 or x is greater than 5/2. What looks like this little thing, curly bracket? That's a curly bracket. It's not a 2. Yeah, if you chopped off the top part of it, it would look like a 2. But we have a little top. It's a curly bracket. Interval notation would go from -infinity up until -3, union 5/2 to infinity. All parentheses. Now, we're not even going to view the graphing calculator. We're just going to sketch it. Given that we have roots at -3 and roots at 5/2, and given that the a value is 2 to this quadratic, does this parabola open up or open down? Opens up. So when is this parabola greater than 0? When is it positive? When is it above the x-axis? All of those things. You see how the solutions present themselves if you're looking at a quick sketch. Okay? So from -infinity up until -3, and from 2.5 up until infinity, we are positive. Okay? So if you like that way better, you can do that. As we get to more difficult polynomials, you guys actually did do this last year, didn't you? You sketched them and looked at where it was above and below. I forgot Mrs. Ziggy teaches that a little bit differently than I do. But that was more to figure out just the graphing of how to graph a polynomial, right? You weren't doing inequalities. But the concept was the same. When is it going to be above? And you would just do a quick number line test and see when it was positive, so you knew the graph was positive in between two roots. So same concept, you just didn't use it to solve inequality. So you have sort of done this. Nope, I was just showing both. You just needed to get the right answer. If you do it via this way or this way, you're good. Rationals, because you guys don't like to sketch rational graphs, I would say that you're probably going to adopt the number line way with that. Fine. All right, here's a larger degree polynomial. Same idea, get it equal to 0. And solve it by factoring, if we can, which we can. Pull out an x squared, you're left with x plus 1. Pull out a negative 4, you're left with x plus 1. We have x plus 1 and x squared minus 4. And then you have x plus 1, x plus 2, and x minus 2 from our difference of perfect squares. Did you get all that covered? So your roots, and what I would do on a number line would be plot negative 1, plot negative 2, plot positive 2. And when I put a point at each of those, is it an open circle or a closed circle? Closed, because we're using less than or equal to. So we could actually equal these numbers, and so they are solutions. And then when you have 3 roots, it produces 4 different intervals that we have to test. Okay? So first with a negative 3. If I plug in a negative 3, it's going to be a negative times a negative times a negative. A negative times a negative times a negative is a negative. Is a negative less than 0? Yes, so that's good. Between negative 1 and negative 2, again, back to the point I made earlier, there's no ideal number to plug in there. But again, we're not going to get wrapped up in the value. So let's say we plugged in negative 1.5. What's this going to be? A negative times, what's this going to be? Positive, what's this going to be? Negative. So what's a negative times a positive times a negative? A positive, and a positive is not less than 0. So as long as you, thank you, as long as you don't get wrapped up in a, in this, getting caught up on the fact that I don't know how to multiply, it doesn't matter. You'll be fine if you just assess negative, positive. Plug in 0, positive, positive, negative will be a negative, so that works. Plugging in a 3, positive, 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 that does not work. So our solutions, I'll just do interval notation, are negative infinity up to negative 2, and a union with the interval from negative 1 to 2. Going back to the alternative way of doing this, which I'm totally fine with, if you wanted to sketch a graph of this polynomial, negative 1, negative 2, and positive 2. Based on n behavior, this is a positive odd, and these are all single roots, so it should start low, end high. So you would just do something like this. And then you would see that this graph is negative over here, from negative infinity up until negative 2, and then again it's negative between negative 1 and 2. Total preference, okay? Any questions here? Okay. So, with rational functions, I think how I want to do this. What sorts of things in rational functions, let me just take a just, I'm going to make up a totally random one. Don't draw this because I don't want you to think it goes with this graph. But if I do that and that, what causes a function to go from being positive to being negative? Meaning, like on a polynomial, what causes a function to go from being negative to being positive is crossing a zero, right? So anytime you have a zero, doesn't always have to happen, right? We could have a polynomial where we have a zero, but it stays negative on both sides. So double roots and so forth, you'd have to be careful of. But the potential possibility to go from a negative to a positive on polynomials is when we have a zero, right? It's negative, it's positive. So on either side straddling a root, you might be negative to positive or positive to negative, right? What on a rational function causes you to go from the graph being a negative to a positive or vice versa? Do the roots still cause that to happen? Here's a root. It was negative on one side, positive on the other, right? But what else can cause your graph to go from being a positive to being a negative? The asymptotes. Okay? On the whatever this asymptote is, just to the left of it, we're positive. Just to the right of it, we're negative. So when it comes to coming up with your critical points, we'll call them, your critical points that are going to create these intervals that you have to test, come from roots and asymptotes. Vertical, right? Horizontal we don't care about. Intervals for inequalities are all your x. We're solving for x here, so we only care about our x coordinates. So what we're going to do here is we're still going to get this equal to 0. That will give you your roots. Let's look at that afterwards. I like the idea to explore that option. That would be if you're solving an equation for sure, but we can probably definitely use it. But I'm going to keep it similar to the polynomial in that you just get it equal to 0. I'm going to get a common denominator, so put this over 1, give this an x plus 3. So it'll be x plus 1 minus 2x minus 6 all over x plus 3, which is going to be not 3x, negative x minus 5 over x plus 3. Where do your roots come from? Roots are otherwise known as x-intercepts. And so to find x-intercepts, we want to kind of figure out where this thing equals 0. What makes the fraction equal 0? Right, if the numerator equals 0, so that's going to be negative 5 is an x-intercept. And vertical asymptotes come from the denominator equaling 0. So the critical points we have to test around are negative 5 and negative 3. And again, we are not at all going to get wrapped up in value here. If I plug in a negative 6, careful here though, if I plug in a negative 6, what's my numerator going to be? Positive, right? Negative 6 will just be 6 minus 5 is positive. And what will my denominator be? Negative. So is a positive divided by a negative? Negative, right? Is a negative greater than 0? No. Get rid of that section. Negative 4. You plug in negative 4, you're going to get a negative over a negative is a positive. Is a positive greater than 0? Yes. Open circle or closed circle on these? Closed. We'll talk about that. We're going to talk about that. And then beyond this negative 3, you plug in a 0, you're going to get a negative times a positive, which is a negative, and negatives are not greater than 0, so that's out. So Connor brings up a good point. Even though it's greater than or equal to, our vertical asymptote really should never be a solid circle, right? Because the graph doesn't exist there. So how could it be greater than 0? So he's correct. Let's make that an open circle. Not because the inequality says to make it an open circle, but because the fact that it's an asymptote and an undefined. So just kind of an added stipulation to just be careful of when you're dealing with rationals. So this function is positive. Now, you could sketch the graph if you wanted to, but like I mentioned, I think you all don't want to sketch rational graphs unless you have to. This, to me, is the more efficient way of doing it, but just for the sake of curiosity, I'm going to sketch the graph x plus 1 divided by x plus 3 minus 2. And I'm going to see this, okay? So when is this graph? We were looking for when it's positive. So it's positive from whatever that root is, which was negative 5, up until the asymptote of negative 3, and it's never positive again. We see that? Just this little section here. Good? Any questions? So back to what Josh had mentioned. If we do cross multiply, that's going to give us x plus 1 equals, cross multiplying is a way to solve an equation. 2x plus 6. Subtract x from both sides, x equals negative 5. That's going to give you your solution, right, for x. It's going to give you a root, but obviously then you'd have to, on a separate thought, think of that asymptote, which isn't hard. So I'm trying to think if there's any reason that won't work. If you so Josh, do me a favor. Do all your homework with that cross multiplying and see if you run into any like special cases or like, you know, little twists that would just put a damp around that. The cross multiplying? Well, no, I think and my point here is just, it's a good idea. It could save everybody a lot of work if we all did it that way. I'm just a little nervous. I'm trying to think. Here's why I get nervous cross multiplying with inequalities. Because when you cross multiply with inequalities, when you multiply or divide, when you're solving an inequality, you always need to flip the direction of the inequality. And if you don't know what x is, you run the risk of multiplying both sides by a negative number, yet forgetting to switch the direction of the sign. But if you're only, and that would have happened here, but if your only purpose is to find the roots, knowing that's not actually a solution, x doesn't actually equal negative 5, but it's going to give us a root, I don't think there's actually any danger in that. So I'm tempted to say that you can do this to find the roots and then just find your asymptotes just by looking at your denominator. And I do think it will work, and I do think it will save you a whole bunch of time, right? Wouldn't that save you a boatload of work? Right. So I'm like 95% sure that you can do it that way. I just want you to do it that way in your homework and tell me if you run into any problem. I think it's actually going to be less work for you. So you'll be our experimenter. You try that. I also in the past have just tried to keep it consistent with the concepts of polynomials. Get it equal to 0, find your roots, that kind of thing. So that's sort of the reason I've done it that way, but I could be open to change. Okay? Any other questions on this? What's on the back? Oh, not much. Good. This seems out of left field, doesn't it? You guys have seen a gazillion quadratics written in this format. a position function for free-falling objects. So due to the acceleration, due to the gravity, and all that sort of thing, this is the general format of any kind of something was fired, like thrown or whatever, that you've been really seeing since Algebra 1. I don't know if anyone's ever pointed out to you before, probably in physics if you're there, that this coefficient always comes from, in V sub 0, is the initial velocity of the object. Obviously, if you throw something, you know, if a 2-year-old throws something with an initial velocity versus an adult throwing something, a faster initial velocity is going to affect the arch of your parabola, right? As something is thrown up and thrown down. The 2-year-olds would probably look like that, right? So the initial velocity plays a part, and obviously the initial position. So the 2-year-old is actually throwing it from a lower initial position, because their arm is closer to the ground, and the adult is further off the ground. So these two things affect the arch of your parabola. But I think you're all familiar with that anyway, yes? Okay? So when this particular problem paints this picture that a ball is thrown vertically upward from the top of the Leaning Tower of Pisa, 190 feet high, that's your S sub 0. With an initial velocity of 96 feet per second, that's your initial velocity. During what time period will the ball's height exceed that of the tower? Okay, so first of all, our formula is negative 16t squared plus 96t plus 190. That's demonstrating the actual height of the object. We are looking for when that will exceed. Exceed means be greater than, right? The height of the tower, which is 190. So this will be a nice easy one to solve, because when we get it equal to 0, we lose our 190s. It's factorable. Does 16 go into 96?
Yes. 16.
So I'm going to take out negative 16t, and I get t minus 6. When I t it up, I get a t of 0 as a root and a t of 6. I like to just jump on my number line. 0, 6. There's no purpose in plugging in a negative number of seconds at all, so I'm over that. Plug in 1, I get a negative times a negative. A negative times a negative is a positive, so that's good. So we'd shade between there. And if I plug in 7, I'm going to get a negative times a positive, which is a negative, so that's out. This should make sense. You're on the Leaning Tower of Pisa, you're 196 up, you throw the ball, and it eventually comes down. We just found out that it's coming below 196. Whoops. It's coming below 196 at the 6-second mark. 190, sorry. So between when it's thrown and 6 seconds later, that's quite the initial vertical velocity, huh? Or initial velocity. 6 seconds is a long time to stay up. Anyway, any questions on that? Okay. So there's your homework on the bottom.
It never did say the object. It could be a nickel for all we know.
1 through 77, yep, 1's, is that a 5? Yeah, 1's 5.
Like, they could